My name is Ben Starkey, and today I'll be talking to you about Physics 2, Lab 3, Magnetic Field of a Bar Magnet. So just a brief introduction. The purpose of this lab was to study magnetic fields from a bar magnet, which we model as a magnetic dipole. Some principles that we need to know are these two formulas on the left, bottom left here. This is the magnetic dipole on perpendicular and on axis, and these are both approximations, but we will be using them in this experiment. We also have this last formula here, which is a more complicated formula that we use in the computational model. So our result was we were able to compare our lab results to a computational model and see the magnetic field arrows around a magnetic dipole, or just a bar magnet. So to explain the experiment a little bit, we first had to calibrate our phone. So we had to download a magnetometer app and set up the ruler to cancel out Earth's magnetic field. And then we were able to move the phone up and down in different positions to find where that magnetometer was on our phone. So here in the picture, the X is where we're going to take all of our measurements with respect to. So the next part was really we had a spreadsheet to fill out, and we had to measure distances for when the B field was 20, 70, 120, 170, and 220 microtesla, which is times 10 to the negative 6. And so I've pictured this example was kind of our average measurement for when the X component of the magnetic field was 20 microtesla. And we're supposed to repeat this 3 times for all 5 of those magnetic field measurements listed there. So here is just a picture of our spreadsheet. I have all of our data on the left, and then kind of the averages in the blue, and that's what's going to get plotted. And so in this graph, we can actually get some useful data from this graph. So let's talk about that in the results. Our n, which is just from the slope, is going to be -3. It's supposed to be an integer, so it's pretty close. And so we take -3 as our n value. And then our natural log of k, which is just the y-intercept, so that's -14.125. And what we're able to do with these values is we're able to calculate the magnetic dipole moment, which is going to be useful for our computational model. So we know that the natural log of k is -14.125, so doing e raised to that number will be k, so that's 7.33, and we're able to use that in our b bar formula. So we know n is 3, so that's going to be the denominator, and then our radius is just 1 because that's the y-intercept. And so we're able to take this value over, see how it's yellow on the left and yellow on the right, so take that over and compare it to the b dipole on axis, and we're able to calculate our magnetic dipole moment as 3.6691, and that's going to be useful in our computational model, as I just said. So in the coding part, a really big part of it was just making this magnetic field function. So using the formula that was given in the lab experiment, calculating the magnitude of r and r hat to plug it into that, and we're just going to be calling this function for different locations around it. So here, the first two are just locations on axis, so that's those are going to be in orange in the computational model. You'll see this in a second. So those are going to be orange, and this is on axis. And then we have 4 positions which are perpendicular to the axis because it is in 3D. So we can do 4. And then I also did one for the perpendicular component, and that's going to be in purple. So you can see in our computational model here, the 2 orange ones are on axis, and they're twice as large as the blue ones, which are perpendicular axis, and those are also in the opposite direction. So really seeing how this bar magnet acts as a dipole. And then in that purple arrow in the top right there is just the d-perp. And so what we did with that is I took this, as you can see in red at the bottom, circling this vector, finding the magnitude of that and comparing it with the magnitude that we have from our lab results. So from our lab results, our magnitude of the magnetic field from d-perp was about 5.5 Tesla, 5.5 to the -5 Tesla, and the magnitude of our computational results was about 3.4 to the -5 Tesla, so that gives us a percent difference of about 16.33%. And this isn't too bad, but there are some sources of error present in the lab. For example, finding the position of the magnetometer on our phone, we may not have perfectly found exactly where that point was, so our measurements would have been off by a little bit every time we measured, and then also not perfectly canceling the Earth's magnetic field out, so not lining up that meter stick to perfectly isolate just the bar magnet in our experiment. So one of the what-if questions is actually, if the meter stick was laid out without perfectly canceling Earth's magnetic field, what would happen? And really what would happen is just the results would have been skewed. It would have just added the Earth's magnetic field to our bar magnet, and so that kind of the superposition of that, just increasing all of our magnitudes and measurements for the magnetic field, at least. And then if two bar magnets were stuck together and the experiment was repeated, then the magnitudes of the magnetic fields would pretty much double, but the directions would be the same. So just a brief conclusion about what we learned about in this lab. Bar magnets can be treated and modeled as magnetic dipoles, and the distance relationship between magnetic dipoles is the same as with